welcome to Bionics of Surfaces. I'm sorry I've drawn it really badly. Today I want to talk about kinetics versus thermodynamics, which is a fight that we often have. So what we've discussed up till now is thermodynamics effectively, but we accidentally touched on kinetics in our last piece, and so let me explain what that means. Kinetics means the speed that something happens. Thermodynamics is effectively how strongly something happens, and they are not necessarily agreeing with each other depending on the process. So as you were aware of, as you saw last time, let me check. As you saw last time, what we had was a container of methanol with a control of the pressure where I could pump out the air. And what we found was we could pump out the air and the methanol didn't boil, although it should have done. And then I put a stick in and I pumped out the air again, and the methanol boiled immediately. We could get the methanol to boil down to below room temperature, down to below 10 degrees, so it became a chiller. It's effectively how refrigerators work. So why can we get the methanol past its boiling point, in this case by chilling it, by reducing the pressure, without it actually boiling? And why does a stick cause it to boil? So in that case, my explanation was, I think, the stick, if we zoom in on a stick, this is a stick, let's have the stick really big. If we zoom in on a stick, it has little tubes in it where the tree was transporting water. And so we've got these little tubes that are now full of air. So they're all full of air, and there's a stack of them, they all go in the same direction. And that's what wood is effectively. Now when we reduce the pressure, this air tries to expand and starts to bubble out of the end of the tube. And that means that any methanol coming along that would like to boil, because it's past its boiling point, because either it's got too hot or the pressure has gone too low, depending on what we're changing, but it's now in a position where it should boil but isn't, it can then go and make this bubble bigger. The problem that we're trying to insist on is that it's very difficult to make the first bubble, and if we've already got one, it's quite easy to make it bigger. So the question is then, why is that difficult? Maybe that's a good question to ask right now, but yeah, let's do that. So to remind you of that point from last time, if we have a tiny bubble, the pressure inside the bubble is higher than the pressure outside because the liquid, the surface tension, is squeezing it. And the surface tension is the same as the surface tension of a bigger bubble, but the component of the force, because it's a curved surface, the component of the force to the inside is way higher when the bubble gets smaller. And mathematically, it should go up to infinity. It doesn't go up to infinity because the bubble doesn't go to zero size, but theoretically, it should go to infinity as the bubble gets smaller and smaller. So eventually, we get to a size where it gets to the same size as molecules, and then obviously our model breaks down because it doesn't really look like that. However, we're still stuck with the problem, how do we make the first bubble? We had the same problem freezing ice and melting it, that it's comparatively easy to melt ice because there's always water on the surface of a piece of ice. But if we've got water with no ice in it, it doesn't start to freeze until we're far below the freezing point. In our case, it was about 10 degrees, I believe. You can get it lower than that. And eventually you make the first piece of ice and then it grows. If we have the right surface, we can make it seem like it's all already ice near the surface of the container. And then we're doing the same as adding a stick to our boiling methanol. We're getting a piece that is starting out looking very much like ice in that case, and the stick was getting a piece that's starting out looking very much like air or gas. And that allows it to grow from that point, so it doesn't cost it so much energy, And that is where the kinetics comes in, or in this case, where the kinetics comes in. The kinetics, remember, is the speed of the reaction. The thermodynamics is how strongly it goes in that direction. So if we consider our frozen water, for example, we will generate some crystals of ice, and they will cluster together. And in between the crystals of ice, they won't agree with each other because there'll be some kind of crystal structure in here, like this. Just, it's not obviously looking like that, but I've just drawn it as a demonstration. Then we've got a different one here, and maybe a third different one. What would that be? Like this. So we've got 3 different crystals of slightly different orientation. The water in the gap here, obviously it's not a vacuum. The water in the gap here has to freeze too, and that can't be quite so ordered as the water in the crystals, because it has to somehow carry the crystal structure of this to the crystal structure of this. So there's water in the gap that's at a higher energy than the water in the crystals. It's not as ordered. Ooh, my face. So if we take our ice that we've formed, we are not going to be able to get this ice to turn into a single crystal unless we bring it up close to 0 degrees and allow the crystals to grow. That's how we could do that. If we do that, we can end up with one very large crystal. But if we just keep cooling it and cooling it, there is no way for these molecules in here to get into a more relaxed state because they're trapped between these 2 crystals. And both of these crystals is effectively would like to grow, but the temperature is too low for the water in between to rotate to allow it to fit and grow this crystal here. And the temperature is definitely too low for this crystal to melt a little bit so that this bigger crystal can get bigger. Whereas if we're close to 0 degrees, the material in here is actually getting melted probably, or getting very soft, close to melting, and then we can just wobble around 0 degrees and it will get bigger and smaller, bigger and smaller, and it will gradually eat into the other crystal. It doesn't really eat it, but over time the smaller one will get smaller and the bigger one will get bigger, which is necessary, obviously, if we're going to end up with one big crystal. Why do I say this right here? Well, if we're cooling something down and we're trying to get to absolute 0, remember our last law of thermodynamics, I forgot which number it is, says that it should be a perfect crystal at that point. But our whole system is all of this water, which is not a perfect crystal until it's just 1. And so its lowest possible entropy state and energy state would be if it was just 1 crystal and had the lowest surface area possible. But if it's already in this state, it is kinetically hemmed. It can't get out of this state until we warm it up again and give it some energy. So maybe we'll have to think about some kinetics to try to work out why that is. But already, logically, we can see, I hope you can see, that that is a problem that will occur, and we will often end up stuck in a kinetically stable state that is thermodynamically unstable. This state is thermodynamically lower in energy than this one, so our thermodynamics would predict that we would end up here. But if we start here, if we end up here for some reason, we can get stuck, we can get lower in temperature, and then we cannot get back out again without heating it up or doing something else. So thermodynamics doesn't always tell us where we really are, because we can get too cold and then kinetics will stop it. It will be too slow. It won't have enough energy to get back out of the state that it's in. The other common example that I like to use here is diamonds. Diamonds are the unstable form of graphite. So if we have a diamond which has a tetrahedral structure, shitty at drawing tetrahedra. So that's a triangle. This is a triangle. Yeah, that's a really bad tetrahedron. I'm going to try again. Just draw a tetrahedron instead, like that. So the carbon is in the middle and it's connected to 4 other carbons. The lowest energy state of carbon is graphite, where it's in this, where the carbon is in the form of hexagonal sheets. So the carbon is bonded to 3 others in this state, and there's 1 extra electron left over, which forms the collaborative bonding, which is why graphite conducts. But this structure, let's draw the rings like this, this structure is difficult to get to from the diamond structure because we have to break a lot of bonds. All of these atoms are in the wrong place. This atom, this atom, this atom, this atom, this atom, then none of them are in the right place to make a graphite. So we can't just move one. We can't just break one bond and start to make some graphite. We need to break quite a lot. And so what we find is that diamonds don't spontaneously turn into graphite. Although thermodynamics says they should, slowly, in reality they don't. And the real reason for it is the same as the real reason for the ice. So let us try to get there by drawing an energy diagram. So this is our energy diagram. We've got a rather difficult to explain axis on the bottom. Here is the energy. This is called reaction coordinate, so it's the reaction going on, and it includes all things that might happen in a reaction, which is why it's not got a physical it's difficult to describe. So our diamond starts off here. We've got an energy barrier because we have to break quite a lot of bonds and reshuffle quite a lot of atoms before we can start to make graphite. When we make graphite, we get some energy out. It's not actually very much energy, so we come down a little bit in energy. Thermodynamics just tells us where this point is and where this point is. Kinetics tells us how high this barrier is effectively. So we've got 3 factors or 2 factors, depending on whether you call this the difference, but we've got 3 factors in our reaction that will all determine where we get to. So if we've got diamond and it's not very hot, we will be stuck as diamond and we'll never make graphite. It turns out that if you heat diamond up to 2000 degrees approximately, it has enough thermal energy to get over this barrier and it turns into graphite, which is a really not very useful experiment to do. And so people don't do it very often. It's kind of expensive and not very useful. We also have to be careful in that diamond will catch on fire in normal air below that temperature. But if we do it in the absence of air, we can convert diamond into graphite spontaneously, but we have to put energy in to get over this energy barrier, which is causing the reaction to go very slowly. Yeah, let's do that. So it's causing the reaction to go very slowly, and in this case, not at all. Why is there very slowly and not at all? It's the same problem that we had with the bubbles, for example, or the pieces of ice, that when they get down to a certain size, they get down to the same kind of dimensions as molecules and atoms, and then we can't consider it to be a continuum anymore. So our thermodynamics assumes that everything behaves itself and behaves like a general, like all the same, and that there aren't really atoms and molecules. And if we reduce and reduce our set, we end up with a problem. The same problem that we discussed before in this course with temperature. If we have the temperature of an amount of stuff and we reduce the amount of stuff, eventually we get down to a small number of molecules, and we have a problem because it's hard to define the temperature of one molecule. It's hard to define the temperature of 2 molecules because some of the time they're both moving in the same direction, some of the time they're not. When they're both moving in the same direction, they don't actually have any translational energy compared to each other. And so they might have a very low temperature, even though they've got translational energy, because the viewing point is the molecule, and if the other one's moving in the same direction, is not moving. So the normal engineering, general or chemistry type of equation that we would like to use for the speed of a reaction is the Arrhenius equation, which I'll just tell you. The Arrhenius equation is an empirical equation, which means it was measured. So this has the rate equals some constant, which varies depending on the situation, an exponential, so that's e to the power of something to the minus, then an activation energy, EA over, let's have KT, RT. Sorry, I've made it messy, so I'll draw that again. Let's have RT. So this reaction is, oops, that doesn't any better. So it's the activation energy divided by RT. R is the ideal gas constant, T is the temperature. If we use K instead of R, we just have to give our activation energy in per atom or per molecule instead of per mole. I'm going to give it to you in this case as R, because then we have per mole, and that highlights the factor that we just had, that if we have too few molecules, things start to get very difficult to define in terms of thermodynamics. So we'll use RT in this case. A is the Arrhenius constant, which varies depending on the reaction. It can also vary depending on temperature, mostly depending on the reaction. So this is the rate, that's the rate of formation of the product, or the rate of loss of the starting material. So in the case of diamond turning into graphite, it's the amount of diamond being formed in moles per second, or the amount of diamond being lost in moles per second, and the amount of graphite being formed in moles per second. I'm probably not going to be able to cut that, but anyway, the activation energy is the height of that energy barrier that we just drew. In the way that this equation was empirically discovered, it was just a number that you had to find out. And you can find that out by doing the reaction at different temperatures, and that will change the speed. The chemistry rule of thumb, which agrees with this equation, is that for every 10 degrees centigrade or Kelvin, you will get approximately twice the rate or half the rate, depending on whether you go up or down. So, and that comes directly from this type of equation, which you may be familiar with from radioactivity. This is like a half-life equation. So if you have e to the power of something, if you change the numbers here, you get a half-life effect. So if you double it, it doubles, or if you change it by a certain amount, it doubles. That's better. So now I'm going to push that equation across to the side, and we're going to draw this graph for another couple of reactions. So now I've got two reactions which I like to use to define this. The first one is methane, CH4, plus 2 oxygens, goes to carbon dioxide, plus 2 waters. 1, 2, 3, 4 oxygens, okay, that's right. And the other one is an analogous reaction, meaning it's very, very similar. SiH4, which is called silane instead of methane, so it's just the same molecule with a silicon instead of a carbon. Silicon is below carbon on the periodic table, so behaves pretty much the same. Plus oxygen turns into SiO2, which is glass or quartz, sand, plus 2 waters. If we do these reactions, we can see some very obvious differences and very obvious similarities. So the first obvious difference is that this is a solid, So we're going to make a solid and a gas, and here we're going to make a gas and another gas. We start off with a gas in both cases, and it's added to oxygen from the air. If we take some methane and we add oxygen from the air, you should all be familiar with this reaction for all kinds of reasons, but usually from heating your house. When you burn some gas, you discover you have to apply a little bit of energy to get it started. That's the activation energy. So we know that this reaction has activation energy. We add a spark, it catches on fire and carries on burning. This reaction doesn't. This reaction, if we put some silane into the air, it catches on fire immediately. Doesn't need any added energy. We take the silane, mix it with air, and it catches on fire and makes silicon dioxide and water. So how does that look on our graph? So here I've sketched them. They're not actually right, but I've sketched them anyway. There's a much higher difference in thermodynamic energy between the starting and the end point, but you can see that's not actually in our rate equation at all. The only thing in the rate equation is the activation energy. In the case of lighting our methane, however, the heat that comes out heats up the incoming gas and heats up the incoming oxygen, so it changes this value of T for the second step, carrying on burning. So once we get it lit, it will carry on burning because this T is higher, which makes this term smaller because it's on the bottom, and because it's negative a smaller amount is not so bad, and so this will be not as small, and so our rate will be higher. If we take this particular reaction, this is the silane, let's change the pen so that it's obvious. We've got this silane, the activation energy is much lower. In that case, this step, the activation, has nothing to do with the oxygen because that would make no sense. The oxygen is the same in both cases. So we've got our CH, for example, and let's call it H3CH, and this H, oh no, I'll do it with the green one. And up here we've got H3C plus H. So we've broken a hydrogen bond. No, not a hydrogen bond. We've broken the bond to a hydrogen. In this case, we do the same. So we've got H3Si, and we're looking at this bond, and it goes to the same thing, H3Si plus H. And those are both reactive species because they've got effectively a bond that is broken. But it's easy to break this bond. It's hard to break this one. Fire is these things here, radicals, floating around with lots of energy. That's where fire comes from. So then these rearrange with the addition of oxygen to make the products. I put them slightly offset to draw it. They don't have the same absolute energy, but it's the change in energy that's important. And change in energy isn't massively different between these two reactions. The activation energy is. There is obviously a difference in the entropy change because one of the products is solid, but that doesn't have an effect on the rate either. The most important effect on the rate is the temperature. However, we have the elephant in the room. What about zero? If we look at this rate, it doesn't actually ever go to zero. A times e to the minus a number divided by another number, this is a constant, is never going to go to zero. It will get smaller and smaller and smaller as this gets bigger, more negative, but it won't turn into zero. It can't actually be zero. In reality, however, we have the hidden problem of starting. So if we had a continuum and everything was the same and there was an infinite amount of everything, then this would be true. At moderate temperatures where the reaction is going this equation works very, very well. But when it gets down to a very low rate, then it doesn't work very well at all, because we're talking about a very small number of molecules, and then the thermodynamics that is assuming that everything is a continuum, everything is the same, doesn't work very well anymore. It doesn't describe the situation very well, and it's exactly the same as the bubble, because the bubble doesn't go to zero size. It's impossible. A bubble in water can't go to zero size, because the smallest that a bubble in water could be would be the smallest that water, the closest that water can get to each other, which isn't zero. So it cannot get to zero. Likewise, here we can only have one breaking bond. We can't have a half or less of one. So the rate starts to go funny when we get down there, just like homeopathy breaks down as you get down to single numbers of molecules, because if we dilute a solution until we have, let's have a cup. So we've got a cup. Ooh, that's cut out. There we go. That's interesting. So if we have a cup and it's got 100 molecules in it, and I tip half of it out and fill it back up again, it's got 50 molecules in. It might have 48, might have 52, might have another number, but it'll have close to 50. But if I get down to 2, there is a reasonable probability that both of them are in the bit that I tip out, and there are none, or neither of them are in there, and then there will be at 2. So there's only, in fact, it's exactly the same chance, because there are only 2. The probability of getting one or none, getting all or none effectively, is exactly the same as the probability of getting half of them. So then the chances are very good that I'll end up with not the number that I think I've got. This is the same problem. So in homeopathy, you carry on diluting it, and obviously if you do that several times, there is no chance that you have a molecule left, because every time there's a probability that you lose more than you think you have, and you cannot lose a fraction of a molecule. So then it becomes a probability that you even have a molecule. This becomes the probability that we even do one, and then it gets very unlikely, and so the reaction almost perfectly stops. It goes slower than this rate would predict at very low temperatures effectively, or very high activation energies. So our diamond isn't really going to convert into graphite. However, if we convert a tiny bit of it into graphite, then it's a lot easier for it to continue, because it's the starting that is the problem. In this case, it's a different problem. It's making these species, which are the reactive ones. Once they're going, then we can generate our products. If we use them up, which we can do, so in a practical case, if we have a metal container, metal grid, we can absorb these species on the surface of the metal, and then the flame will not go through it. So you will have seen this. If you take a grid of wires and you stream some methane through it, so you stream some methane through it, you can light the bit on one side of the grid, and the flame does not travel through it, because these species tend to get absorbed onto the surface, and so they get down to such a low concentration that the rate goes back down again. It can't make itself hot enough to sustain the reaction. This one, you can't do that, because the moment that you mix this with oxygen, it explodes, it catches on fire. If you mix it in a low concentration, it just burns. If you mix it in a high concentration, it explodes. If we were to cool it down to a very low temperature, below room temperature, then it would go slower, and then you could have to light it. You could light it maybe by touching it with your warm finger. So I don't know what the temperature is when you can stop this working. What does that tell us? It tells us that this number is important. RT is an important number, because if we have the activation energy divided by RT, we end up with 1. E to the minus 1 would be our starting point, and that is also a rule of thumb of when the reaction is really going. Below that temperature, it's going to be mostly stopped, and above that temperature, it is mostly going, but that is only an approximation because it depends on the mechanism how easy it is to stop it. Let's take another example where kinetics is winning over thermodynamics. If we take sugary water, whoops, there's my finger. If we take sugary water and we leave it lying around, we don't see that it converts into carbon dioxide and more water. If we leave our Coca-Cola lying around and the carbon dioxide bubbles out, it doesn't boil out, the carbon dioxide bubbles out and oxygen dissolves into our Coca-Cola, it becomes disgusting, but it doesn't become not sweet, even if it's the sugar version. It doesn't become not sweet, even though the reaction of sugar and oxygen is incredibly energetic. It's thermodynamically extremely strongly favored. But kinetically, it's difficult, and that is what we use, what most of life uses, as a way of dealing with energy, because we can store energy as sugars, and then we can oxidize it in a different way, using a catalyst so that the activation energy is lower, so the reaction can then go at normal temperatures, at body temperature, and then we can go back and stop the reaction when we don't need it. This is a very common way of stopping reactions and very useful to us. All right, let's introduce our last subject using this one. So if we take, for example, a drop of water on the window of a house, this is the window of the house, well, can't draw straight while I'm looking away, and a drop of water, what we can see typically is that the drop of water hangs there until it reaches a certain size, which is exactly the same thing that's going on in our reactions. There's effectively an activation energy. It comes from a different physical mechanism, but there's effectively an activation energy that prevents the drop of water from attaining its thermodynamic equilibrium, which would be down at the bottom here. That's what the drop should do thermodynamically, but it's not what it does in reality. It will sit here until it evaporates, unless we make it bigger or shake the window to make it go down. We often see this happen. We will look into that in our last topic, the actual drops on surfaces part, which I will do next time, in which we look at why or how a drop sits on a surface in different ways. We could have one that sits like this, or if it was more hydrophobic, let's draw another one to do that. If it was more hydrophobic, it might sit up more instead. And those differences are dependent on differences in chemistry of the surface and differences in the water drop, but we can still get stuck in a kinetic situation where it's stuck and waiting. Likewise, if we take, for example, a small drop and a big drop, and we leave it, they will both evaporate, but because the pressure inside the small drop is higher than the pressure inside the big drop, the small drop will evaporate faster, and if we cover it up, the small drop will evaporate and the big one will get bigger because it will be absorbing water from the atmosphere faster than it's losing it. If we then add a flat piece or a cold surface, it will draw all of the water away. But if we have a small drop and a big drop, the small drop will get smaller and the big drop will get bigger. This effect is exactly the same as the ice crystals. So before we stop, I'm hoping that I've got my sound on. Yep. Before we stop, we'll look at this last situation where we've got a starting situation with small drops and big drops. We could imagine this as crystals of ice in water, or we could imagine it as crystals of salt in water again, forming from water, or we can imagine it as drops of water on a surface, with the rest being air. What will happen to it? Well, we know what the thermodynamic answer is. Thermodynamically, let's go right over here. Thermodynamically, we would have one particle at the end, and it would be as spherical as possible. Oops, that's right behind my head. It would be as spherical as possible without generating, without sacrificing energy in some other way. So if it was crystalline, it would not be quite spherical because it's cheaper energetically to make crystal surfaces. But if it's not crystalline, a drop or something, then it would be almost perfectly spherical. That would be the thermodynamic endpoint, but we don't necessarily get there because we don't necessarily have enough kinetic energy. We don't necessarily have the activation energy to get there, so we get stuck kinetically. That's what I want to say. On the way there, however, we can see what's going to happen. The smaller ones are going to disappear. They're going to dissolve into solution or evaporate if they're drops, or melt if they're frozen. And the bigger ones are going to net absorb them, and that was because of the surface tension effect, because of the surface effect, which is an extra effect that we like to ignore in our thermodynamics, but it is there. And that was making this lower in energy than this particle. So although they're both particles of the same stuff, they have different energies. And now we will first of all lose the tiny ones. So they will first of all disappear, and then the next ones will disappear. And so our intermediate step will have 3 of approximately equal size, because there are 3 mid-sized particles in there. When we get to that step, it's relatively balanced, and until one of them starts to win, each one is dissolving at the same rate that it's reprecipitating, or if they're water drops and they're enclosed, each one of them is evaporating and water is condensing on them. When it evaporates, it gets a little bit colder because it loses a bit of energy. When it condenses, it gets a little bit warmer because it gains a little bit of energy from the bonding forming, and that causes it to not change in size effectively, because if it loses volume, it gets colder, and that will tend to make it absorb more, which will make it warmer, and then it will tend to make it evaporate more, and so it will automatically stop changing size. These ones would try to do that, but if they're big, there are big differences in size. This can lose almost all of its volume before it gets cold enough to stop evaporating, and then it won't collect enough to grow back again, and this one will just swallow it effectively. This is a step which it can get stuck at for a very long time, so that's the kinetically stable state, where it will stop and could last. We can harvest this. This isn't often used to make particles of much the same size, or oil drops in water of much the same size, because if we leave this to stand, it will ripen, and the ripe state is where they're all the same size. So this can be of practical use. This is called Ostwald ripening, and it allows us to get rid of the starting state if we have physical difficulties making our particles all the same size, if that's the goal. If we want them to all be different sizes, then we have to protect them from dissolving, evaporating, melting, depending on what they are. Okay, so I've thought of 2 topics that we need to do now. We need to cover the bonding between water molecules and other water molecules, the bonding inside molecules and the bonding outside molecules, because I think we didn't cover that well enough before. And we also need to do drops on surfaces, and that will be the end of our course. That's good because we haven't got very much longer left. So those are the topics that we will do for the rest of the time that we have. I will see you next time. Hopefully it won't be too long this time.